Hello and welcome to Physical Sciences 3. You should hopefully have a booklet in front of you with this title on it. So it's Units, Significant Figures and Scientific Notation. And it's got a few pictures on it as well. So these topics here might not seem like the most exciting ones to start a unit with, a school year with, but they are very important, as outlined by this famous example where units were mucked around. So this here is the Mars climate orbiter, and in 1999 it was launched as seen in this picture here. And the problem with this one was there was NASA, and they were working with a company called Lockheed Martin, who are a very famous company, and their logo is the basis for the Stark Industries logo in the Marvel movies as well. Lockheed Martin are basically a weapons company and technology company, and they work with NASA. And the problem that happened here in 1999 was that they had a piece of code, and one of them had one type of unit in it, and the other code that was working with it had a different type of unit in it. And so what happened when they launched it into space is every time they made an adjustment to the trajectory of the spacecraft, it was a little bit out, and all their readings they got back were incorrect. And eventually the Mars Climate Orbiter just cannoned into Mars and was destroyed, costing a lot of money. Okay, and I've got this picture down here as well, just because I like it. I think it's a nice picture. Alright, moving on. So, we're starting off with measurement and units and introductory theory, and these three measurements here would be fairly common to you. So, we've got the mass of a beaker is 101.73 grams. We might have a volume of a solution is 50 mils, so mils you would have heard of, grams you would have heard of, and obviously temperature 24 degrees Celsius. So they're kind of typical units that we might use every day. But in science we need to have a kind of a uniform standard, just to try and avoid things like happened with the Mars Climate Orbiter. And so we have a measurement called the Système International. It's a French system, and my French is terrible, so just excuse me there. So it's Système International, or SI, we just call it the SI units, and it has 7 base units for measuring any physical quantity. So here we have listed 6 of them, and we've left one out called candela, because that's for luminous intensity, and we don't use that in this course. So the 6 ones we will use in this course are these ones here. So for mass, and we will talk later on about the difference between mass versus weight. So mass versus weight, they are not the same thing, but you might think of, at the moment, what you think of as weight is actually mass. So we'll talk about that later on in the course. But mass is measured in kilograms, time is measured in seconds, length is measured in meters, electric current is measured in amperes, temperature is measured in kelvins, and amount of a substance is a mole. And we'll talk about all these in detail later on. But these 3 here, you'll probably be familiar with anyway: kilograms, seconds, and meters. Okay, so they're our base units. Then we have these things called derived units, and they are units which are based on the base units. So we have volume here. So if you have a cup or a drink bottle or something like that, the volume of that can be measured in meters cubed. Okay, velocity, which is similar to speed, is measured in meters per second. So if you're in a car, you typically have measurements of kilometers per hour, but the SI unit for velocity or speed is meters per second. We have these things called density, kilograms meters per second. Kilograms per meter cubed. Acceleration is meters per second squared. Force, kilograms times meters per second squared as well. Work or energy, I shouldn't go through any of these anyway, but they're all here like that. And I just want to highlight here, if we have something like meters per second, so this little -1 is the same as meters divided by seconds, like that. Similarly, you might have seen kilometers per hour is equal to kilometers per hour. So when we see this little -1, it means divided by, like that. So kilometers divided by hours, or per hours. Okay, so just note that when the derived units have a person's name, such as a force, the derived unit is written in full using the lowercase and not the capital letter. The capital is used for the abbreviation. So when they're talking about force here, the force has been named for Isaac Newton, who was a famous scientist who made a lot of discoveries. And so rather than writing out kilograms meters per second squared each time, we just write out a big capital N for that unit. Or in electrical charge down here, this one has been named for Coulomb, and instead of writing out 125 coulombs each time, we write out 125 C. And just here, another note for chemistry. The normal unit for volume used by chemists is the litre, and the capital L is used because the lowercase l is too easily confused with the number 1. So 1 litre is equal to 1,000 millilitres, which is equal to 1,000 centimetres cubed. And we're going to go over all this later on in the course, so don't be alarmed if this is a bit of information overload to start off with. You don't have to remember all that. These are all on the formula sheets as well, so do not stress. We're going to move on to powers of 10 next, and unit prefixes, and we might cover that in the next video.